we saw that it's partly kinetic and then potential. So these two add up to form the mechanical energy reserved by the body. For a loaded spring, for a loaded spring, its kinetic energy K is given by half mv squared. The usual kinetic energy formula, but we substitute into the equation velocity of a body executing simple harmonic motion. V squared is given by omega squared a squared minus y squared. And this we can substitute into the equation of how omega squared minus y squared. We use this to deduce the fact that maximum kinetic energy when y is 0. So when y is 0, we have the kinetic energy being equal to half m omega squared a squared. For springs, because the spring constant k is equal to m omega squared, we can also say that ke max is equal to half k a squared. That is the expression of maximum kinetic energy. Minimum occurs when y is equal to a. Now, before we look at the minimum, we are reviewing what we went through last time. So a half k a squared. This we saw that maximum kinetic energy occurs at the what? Where does it occur? The maximum Ke, where does it occur, class? Where? Ama, Adua, Charlotte, Stephanie, where does it occur for my equation? Where does the maximum Ke occur?
Mean point.
At the mean point.
So, occur at the mean point. The reason for which we said y is equal to 0. So, the Ke minimum occur at the what? Where does maximum kinetic energy occur? Where does it occur?
At the extremes.
At the extreme. And at the extreme, the displacement is equal to what?
Amplitude.
Amplitude.
So y is equal to a. So if y is equal to a, then we have Ke minimum being equal to half, it's even equal to 0 because half m omega squared a squared minus y is equal to a, so a squared. Therefore, this is 0. And the minimum kinetic energy of an oscillating body is always equal to 0. Then we look at potential energy. But here for springs, we're talking about elastic potential energy. Elastic potential energy. Gravitational potential energy applies to a simple pendulum. And here we look at a spring on unloaded spring and then a loaded spring. For unloaded spring, the restoring force F is equal to 0. And for loaded spring, the restoring force F is equal to F. The restoring force is equal to Hooke's law. So F is equal to K X or Y. So we define the elastic potential energy as the work done in stretching or compressing the spring. And this is also equal to the energy stored in the spring. So the work done in compressing or stretching the spring is also known as the energy stored in the spring. So what is this work done? Work equals force times distance. But the distance here is the extension within the spring. So the extension X. Here the force is the average force. So we look at the force on the spring when there's no load, and then which is 0, and then the force on the spring when there's load. This is the restoring force. Now, the average, we must sum these two forces up and divide by 2. This times the extension X. So we have the average force to be F on 2 times X. Now by Hooke's law, what is F? F is K times X over 2 times X. So we have the work done equal to half Kx squared. And this is the elastic potential energy. So for a loaded spring, its elastic potential energy, which is the energy stored within a spring, is given by half of the spring constant times the square of the extension, which is actually a displacement. And so we realize that for elastic potential energy, E, the potential energy is directly proportional to x squared because K is a constant, half is a constant. Now, let's look at where maximum and minimum potential energy. We are calling it potential, but we must understand this is about elastic potential energy. This we can also express as half m omega squared x squared. This is because K is equal to m omega squared. So where does the maximum potential energy occur? It will occur at the extreme where displacement x is equal to the amplitude. So E maximum will be equal to half m omega squared A squared and occur at the extreme. At the extremes. Now, minimum potential energy E minimum occur at the mean point where the extension or displacement is zero. When x is equal to zero, minimum potential energy, elastic potential energy occurs. And E minimum will be equal to zero because then we determine the total energy possessed. Total energy, which is the mechanical energy, we saw to be equal to kinetic energy plus the potential energy. I still repeat, this is for springs, for loaded springs. If it's a simple pendulum, the expression will change. I took you through last time. So if E total, therefore, is equal to half m omega squared a squared minus y squared. Then we change the elastic potential energy, which is half omega m omega squared times y squared. Then we add. When we add, we realize that the total energy is given by half m omega squared a squared. So the total energy through is a function of the amplitude, the square of the amplitude. So it means that total potential energy occurs at the extreme, and the total mechanical energy of an oscillating body also occurs at the extreme. Okay. So this is the summary of what we did. Then the energy graph in terms of displacement. Here we're talking about energy graph in terms of displacement. In terms of displacement. So here we look at an oscillating body. Just one extreme, another extreme. Oh, here we are plotting the energy at the extremes and energy at the minimum point. So let's plot this vertical line or line indicate the energy. Now, for an oscillating body, its energy is maximum. Potential energy is maximum at the extremes. So potential energy, oh, I'm coming in. I want to change this earpiece. It's giving me a signal. So let me change it and then get back to you. Then that's fine. So
We are looking at kinetic energy at the extremes, potential energy and kinetic energy at the mean points, potential energy at the extremes, potential energy at the mean points. So for PE, it is maximum at the extremes and minimum at the mean points. So this is potential energy. This is the potential energy. Then kinetic energy at the extreme is minimum and it's maximum when crossing the mean point. So it's 0 here. Then by the time it crosses this, it's minimum. Getting to the other extreme, it must be decreasing to 0. It's a curve. So this is KE. A line connecting the two graphs gives us the total energy possessed by the body, which is its mechanical energy. So this is E total. And this represents the energy interchanging graph in terms of displacement. Where they cross each other. Amma.
Sir, can you continue, then I'll ask my question.
Pardon?
Please continue. I'll ask my question later.
Okay, so where the two graphs intersect, we have, meaning at this point, we have equal, KE and PE are equal. At the intersecting points A and B, PE and KE are the same. And don't forget, an increase in one form of energy is a drop in the other form of energy. Okay, or a loss in one form of energy is a gain in the other form of energy. There is another graph. Don't forget, this is energy graph with respect to displacement. There is another graph which is in terms of time. Energy graph in terms of time. What we have here is energy graph in terms of displacement. So with this graph, we are plotting energy on the vertical axis as against time on the horizontal axis. Now, how do we plot this graph? So energy. So we are going to, the energy possessed is actually KE and PE. And The combination of KE and PE gives us the mechanical energy, the body's mechanical energy. But we have seen these energies in terms of displacement. So we must express these energies in terms of time for us to be able to plot energy and time graph. How do we do that? So KE is equal to half m omega squared a squared minus y squared. We can express, and this is kinetic energy formula in terms of displacement, because omega and a are constant. The mass is also constant. So the only possible changing variable will be displacement. If we are considering oscillation along the vertical axis, and along the vertical axis, the displacement in terms of time is equal to a sine omega t. So let's substitute y which is this, in place of what we have here. We will have KE is equal to half m omega squared a squared minus a sine omega t all squared. So that when we expand this, we have half m omega squared a squared out 1 minus sine squared omega t in. Because when we simplify what is within the bracket, we have a squared and sine omega t squared, which is actually written as this. Now, what is 1 minus sine squared omega t, class? What is it? 1 minus sine squared omega t.
Cos square omega t.
So that is cos squared omega t. So we have half m omega squared a squared cos squared omega t. And this is a kinetic energy formula in terms of time. So we are going to use this to plot energy against time, kinetic energy against time. Let's look at how potential energy would also be. Elastic potential energy is given by half m omega squared times y squared. Since we are looking at oscillation along the vertical, y squared will be a sine omega t all squared, meaning we are only substituting the trig function of y there, just as we did for kinetic energy. So we have half m omega squared a squared sine squared omega t. It therefore means that the kinetic energy is in terms of cosine, whereas the potential energy is in terms of sine. So we'll use these two trig functions to plot energy against time. Now we will do it for one cycle. And the time taken for a body to make one complete cycle is the period. So let's divide period into 4 parts: quarter, half, 3/4, and then so quarter, half, 3/4, and then T. So this is quarter of the period, half of the period, 3/4 of the period, and then capital T. Please do not forget that this can also be expressed as angle: 90, 180, 270, 360. Let's plot the kinetic energy first. Now this value, the coefficient to a trig or cosine function, is always known as the what? What is the coefficient to the trig or the cosine function? What name do we give to it? What name do we give to that?
Amplitude.
The amplitude. So this is the maximum, and the amplitude is the maximum displacement. Since this is not displacement, we will call this as the maximum kinetic energy. Okay, so the maximum kinetic energy is this. This is the maximum potential energy. So when the body is oscillating, the body moves in between these extremes, maximum values. So we have maximum potential energy, half m omega squared, which is also the same as the maximum kinetic energy. Okay, but we have one up here and then another one down here. So it will oscillate between these two limits. So minus half m omega squared a squared a squared. Now we are plotting kinetic energy first. When T is equal to 0 or theta is equal to 0, what will be the kinetic energy? So we are starting from when the time is 0 or the angle is 0. When T is 0 or the theta is 0, what will be Ke? Yes. Calculate and share with me. If T is 0 or theta is 0, what will be Ke? Anybody?
Maximum.
Pardon?
Maximum.
It will be equal to maximum. So it will be equal to half m omega squared a. So when this is 0, it will be equal to energy, kinetic energy will be equal to the maximum value. When T is quarter of the period or theta is 90, what will be kinetic energy? When T is quarter of the period or theta is 90, what will be the kinetic energy?
0.
That will be 0 because cos 90 is 0. And when you square 0, it's still 0. So this will be 0. Energy, kinetic energy will be 0. When T is half of the period or theta is 180, 180 degrees. What will be the kinetic energy? When T is half of the period or theta is 180, what will be the kinetic energy?
It will be negative.
No. It will not be negative.
It will be maximum, but a negative sign attached.
No. That will not be it. Nanama and go ahead, watch and then tell me what you also think.
It will be positive 1.
It will be positive. Ama, it is, look at it. We have cos squared omega t. This is the same as cos omega t all squared. So when you put in 180, you get -1, but it's a square. Do you get it?
Yes, please.
It's a square, so it will be positive of the maximum value. So this time or angle would go with an energy value equal to the maximum. When time is 3/4 of t or theta is 270, what will be the energy?
0.
0. If time is capital T or theta is 360, what will be the energy?
Positive 1.
So don't forget, this will give you +1, but times this, so it will be equal to the maximum kinetic energy. Say it as such rather. Is that okay?
Yes, please.
So when you join the points, kinetic energy will look like this. So this graph is for KE. Kinetic energy. Let's also plot it for potential energy and see how that will change. I want to change the marker. Good. So we are going to plot it for potential energy using this equation this time around. So we earlier did that for one cycle. We are doing it for one cycle. Now, meaning we are plotting both KE and PE along the vertical. So E, KE, E. For potential energy, when the time is 0 or the angle theta is 0, what will be the potential energy? When T is 0 or theta is 0, what will be the potential energy?
0.
That will be 0. Sine function starts from 0. When T is quarter of the period or theta is 90, what will be the potential energy? Yes, I'm
At the
listening.
maximum.
At the maximum potential energy. So This time we'll go with energy of at the maximum value. When theta is 180 or half, time is half, what will be the potential energy?
0.
So 0, then maximum 270 would be equal to maximum because we have -1, but when you square it will be positive. So maximum, and this will also drop to 0. When theta is capital T, or when theta is 360, or T is this. So when you join the point, this is what you have. This is also for PE. This is PE, whereas this is KE. Now, the line joining the two graphs is the total energy. Similar to what we are also seeing here. So this is the total energy, E total. Now watch that here, the negative amplitude didn't come in because the negative did not show. This is because both cosine and kinetic energy and potential energy are square. They are squares. So even when you get a negative value, it will be squared. The reason for which it is not oscillating between the negative amplitude and then the positive amplitude, but it's just between 0 and the positive. Please, are we okay?
Yes.
So this is the energy graph in terms of time. This is the energy graph in terms of time, whereas this one is the energy graph in terms of displacement. This is actually for half cycle, because if we are drawing it for one cycle is such that it must move from one extreme to another extreme and return. Meaning if we are starting from here, it must go and then come 1, 2. But because it is here, from here to here, this is for only half cycle. This is for one cycle. Okay, if you look at this critically, this part we are seeing from this point to this point can be obtained here, from this point to this point, from this point to this point. Then the turning point of this is not good. Let me perfect it. The turning point. Good. So this and this can be seen from here to here. Then we have from here to here. So this is for one cycle, whereas this is for half a cycle. Please, any question? So we have this as the energy graph in terms of displacement. Okay, energy interchangeability, potential to kinetic, kinetic to potential. At the extreme, total mechanical energy is equal to the potential energy. At the mean point, total mechanical energy is equal to the kinetic energy and vice versa. And over here, in terms of time, where the two graphs are intersecting, then it means we have both energies being the same at that point. So for one cycle, if we are to label it A, B, C, D, these are the points where the total energies are the same. Mechanical energy equals potential energy at this point. So this is the ending of simple harmonic motion. The ending of simple harmonic motion. Hold on, let me look for 2023 paper. There was this question under simple harmonic motion. Let me define simple harmonic motion. Then I sketch a displacement time graph for a simple pendulum sketch a displacement time graph for a simple pendulum undergoing a large angular displacement for two complete cycles. Then the D question is that a body of mass 100 grams performs a simple harmonic motion. With an amplitude of 4.0 centimeter. If it completes 20 oscillations in 15.0 seconds. Calculate I, the minimum velocity attained. II. Total mechanical energy at the equilibrium position. Take power squared to be equal to 10. This is the question under SHM. Question I. Okay, so Adoma, Akuya, Amma, Effie, Lynn, Anama, and Stephanie. I saw Lizzie. Lizzie is gone. Define simple harmonic motion. As for this, if you are here and you can't define it, then it's serious. It is the repeated to and fro motion or to and fro or up and down motion of a body. Repeated to and fro or up and down motion of a body. Okay. Around a mean point or a fixed point whose displacement is directly proportional to the acceleration but oppositely directed or always directed to the mean point. Now sketch a displacement time graph for a simple pendulum undergoing a large angular displacement for 2 complete cycles. In pendulum experiment, one of the precautions is that when you are displacing it, you don't displace it wide, at wide angle, angular displacement. No. We don't do this. Give it small angular displacement. And if all factors that would reduce its amplitude of oscillation isn't there, then the time taken for any complete oscillation will be the same. You see, when you give it small angular displacement, it will be oscillating freely. What is free oscillation? In free oscillation, when the body is in that periodic movement, its amplitude of oscillation does not reduce. So, assuming I give it this amplitude, this is the mean point, meaning this distance from the mean point to it is my amplitude. Now, if it is oscillating freely, at every movement, it must go and return to this same point. Assuming my hand is that point, it must move from the mean point, go and come, reach it at any time. When it doesn't get to it, then it means the amplitude of oscillation is reducing. And that is the effect when the body is given large angular displacement. So when you displace it, it will be loosened. But when you give it small angular displacement, it will be oscillating freely and will maintain the amplitude and the period of oscillation every time. So if you give it small angular displacement for 2 cycles, this is how the displacement graph, okay, displacement time graph will look like. YT. We are drawing it for 2 cycles. So in terms of angle, maybe 90, 180. If we are doing it in terms of angle, 270, 360, plus 90, 450. Plus 90. Plus 90.
5,
Plus 90.
6, 30,
Plus 90.
7, 20.
So this angle, if you are doing it according to time, then it will be quarter T, half T, 3/4 T. Okay, T plus quarter. So 1 plus quarter.
5 on 4.
5 on 4 plus quarter, so you get to 2T. So if you are doing it according to time, this is how it will be. Now, displacement time graph for oscillation about the vertical axis. The maximum will be A. Minimum will be minus A. And so this will be 0 when T is there. 0, maximum, minimum, maximum, but in the opposite direction. 0, maximum, 0, minimum in the maximum but in the opposite direction, and then 0. So when you plot this point, you have so this is displacement time graph for 2 cycles. For 2 cycles. And this is when the motion is given small angular displacement or small angular displacement, or when theta is small. So the body will be oscillating freely. Now, if you give it a large angular displacement, this is how the graph will look like. Let me clean. Oh, where's my liquid to clean? Okay. So here the amplitude, the oscillation will be damped. When oscillation is said to be damped, then it means as the body oscillates, the amplitude of oscillation reduces. So in damped oscillation, the amplitude of oscillation reduces exponentially. But in free oscillation, the amplitude of oscillation is maintained throughout. So let me draw the displacement time graph for damped oscillation, where the body is given large angular displacement. Okay, so once it's against displacement time, so T must be time. But for easy identification, the reason for which you can switch it to angles. Plus quarter. Plus quarter. Plus quarter. This is 2T. It's a displacement time graph. So now here the body's displacement starts with a very large amplitude, Y. And as the body oscillates, its amplitude decreases. So at T, 0, at quarter, we have maximum. At this 0, at 3/4, yes, but you realize that naturally the amplitude of oscillation will be decreasing. So it will not exactly get to where it's supposed to be. Then come to 0. Then the same thing. Drop to 0. This will also, the amplitude will decrease. Then when you plot the points, this is what you see. And look at what is happening. We are starting with very large amplitude, but as the motion goes on and on, the amplitude will be dropping. If there is a third cycle, you realize that by the time it gets to the third cycle, it has decreased so much. This is what happens, but please, the question asks us to end at for 2 cycles. I'm just including this for a better understanding. Please, are you okay?
Yes.
So this is what happens when a simple pendulum is given a very large angular displacement. When it is given a very small angular displacement, this is what happens. This is the displacement time graph. And this is, so this is free oscillation. This one is free oscillation, but this one is damped oscillation, where the oscillating body loses energy to air resistance and friction. Please, any question? All right, then let's look at ma'am.
Sir, please, could you also Start drawing the graph from the amplitude.
No, you see, it's a displacement time graph. So I'm assuming that it is oscillating along the vertical axis. The reason for which, fine, you can also use cosine if you are looking at the oscillation along the horizontal axis. Is that okay?
Okay.
And it will be
Yes.
the same thing. All right. So the next question is D. A body of mass 100 gram performs a simple harmonic motion with an amplitude 4 centimeter. If it completes 20 oscillations in 15 seconds, calculate the minimum velocity. And then the total mechanical energy obtained at the equilibrium. We won't even waste time. The minimum velocity of an oscillating body is always 0. Because at the extreme, it occurs at the extreme. And at the extreme, the displacement is equal to the amplitude. So when you use V is equal to omega times square root of a squared minus y squared. Okay. Minimum velocity occurs when y is equal to a. So if y is equal to a, then this will be a. So the amplitude is 4. 4 squared minus 4 squared. We don't even need this because it will be 0. Okay. So if you want to show working, omega must be, because you know that the minimum velocity will occur at the mean extreme. And at the extreme, this is it. So 4 squared minus 4 squared. 16 minus 16. So you don't even need to calculate for this, and you are there. Answer is 0. So this is even a question that it does not demand calculation. You can put 0 there and explain. I. Listen to this question. Calculate the total mechanical energy at the equilibrium position. Now, class, at the equilibrium position, what will be the total mechanical energy?
Kinetic energy.
That will be kinetic energy. Okay, because at the mean point, potential energy is 0, kinetic energy is maximum. So when I determine maximum Ke, K maximum, which is half m omega squared a squared, I'm there. Then the mass is 100, so times 0.1. Angular velocity is 2 omega is equal to 2 pi on t. We are told that if it completes 20 oscillations in 5 seconds, so I will need t, number of oscillations 20, time for that oscillation 15. I can use this to find period. Period therefore will be equal to small t over n, which is 15 divided by 20. And this is equal to 3/4. 3/4 in decimal is equal to 0.75. Right? So, because I will need omega squared, so this will be equal to, omega squared will be equal to 2 pi all squared divided by 0.75 squared. Now, watch this. In the question, you are told that pi squared is equal to 10. So you don't substitute your own value of pi. Use whatever you are given. So it means this will be equal to 4 times pi squared over 0.75 squared. What is 0.75 squared? So let's determine 0.75 squared. This is 0.5625. So let's finish the calculation up here. Hey, am I recording? Yes. So we have omega squared equal to 4 pi squared over 0.75 squared. We got 0.5625. But we are told from the question that pi squared is 10. So 4 times 10 divided by 0.5625 must be our answer for omega. So 40 divided by 0.5625. This is giving us 71.11. 71.11 radian per second squared. Then, having obtained this, you substitute the value into this function times 71.11 times the amplitude is 4. You change 4 into meter, and that will be 0.04. Then you calculate. So this times 0.04 times 0.1, which is this, divided by 2. So you have 0.1422. The kinetic energy, therefore, is 0.1422 joule as the total mechanical energy. So E,
Mr. Yeah,
hello,
please, won't we square the 0.04?
oh, it's squared, thank you. Amplitude squared. So let's go through it again. So 0.1 times 71.11 times 0.04 squared. This is giving us that divided by 2. And we'll have 0.00569. 0.00569. Thanks for the correction. So it's not such a difficult question. You just need to understand the concept of simple harmonic motion, and then you'll be smiling. Okay. Once we've gone through, when you come and then you are doing it, I can be giving you challenging questions to refresh your memory and on that. Okay. So this is whatever came on simple harmonic motion in WASI 2023. Very simple question. All right. So class, I'll put something together for you on Monday. Just simple questions for you to answer to end, okay, the whole Omega session. Okay. So we'll end here. If you have any question, ask before we finish everything. Any question? All right. If no question, then Adoma, Charlotte, Equia, Ama, Effie, Herbert, Nanama, Stephanie, and Yaba. This is where I draw the curtains on today's session. We'll meet on Monday. Take care of yourself and have a lovely weekend. Bye-bye.
Bye.
All right.